Testing. Testing. Yeah, okay, good. You're okay. All right, thanks for coming in after lunch. This is the session on storage and distribution, and we have three interesting papers today, two research track papers and one industrial paper. And to start it off, I have Hachuan Bian here, and he'll be telling us about column ordering in analytic databases. Take it away.
Okay, hello everyone. I'm Hao Chongbian from Renmin University of China. The problem we solve in this paper is how to reorder the columns in for a white table stored on HDFS. This is a joint research work with Microsoft Research. As we all know, HDFS has become the common storage engine for a lot of data analytic systems. A table stored in these systems is stored as a set of HDFS files with specific file formats such as text file, sequential file, or RC file. As there are more and more data analytic applications in these systems, the tables have become wider and wider. Tables with hundreds or even thousands of columns are often seen. With these wide tables, we can avoid doing the distributed joins of large data sets because this is very expensive in Hadoop environment. Wide table stored on HDFS is stored as a set of row group. Each row group is usually stored in one HDFS block. Inside each row group, data is stored in columnar manner, and there's a metadata header or footer to store the positions of each column trunk and some statistic values of each column trunk, such as the mean and max values. A query executed on white table looks like this. When executing the query, a set of or one computing task will be launched for each column for each row group, and it will read the columns needed by the query one by one. Why we use column store on HDFS? The reason is that column store can help us improve the I/O performance, because with the column store we can skip the irrelevant column trunks, so the I/O cost is reduced. And with the column store, we have better compression ratio. So far, everything looks so good. We have fault tolerance, we have good scalability, and we do not need to perform distributed joins, and we have very good I/O performance. But actually, we can further improve the I/O performance by reducing the seek cost. Here's an example. Giving an initial column order, query Q1 with 4 columns in a row group. There will be a seek before it reads the next column. And for query Q2, things are similar. This column, these seeks will be expensive if the data is stored on hard disks. Here we perform an query in the real environment. We have 400 gigabytes data stored in Parquet format. Parquet is a popular calendar format on HDFS. The data has more than 1,000 columns. We have a Spark query which accesses 8 columns. The summation volume of the 8 columns is 1.2 gigabyte. Ideally, the read latency will be only 12 seconds. But actually, the read latency is more than 900 seconds. This is because the seek cost overhead. To further prove that seek cost really matters, we run 3 queries in real production environment. For each query, we manually put the access columns in front of the column order. So we can see the end-to-end query latency is reduced by 73% on average for the 3 queries. So we have to define the column ordering problem and try to solve it. The problem can be defined like this. We define what is the seek cost of a query and what is the seek cost of a workload. So the column ordering problem can be defined as given a workload queue, how to find an optimal column order as star such that the seek cost of queue is minimized. And we can prove that this problem is NP-hard. The first thing we should do to solve this problem is to get an accurate seek cost function. Getting the accurate seek cost function is challenging because disk manufacturers does not tell us many parameters of the disk in their manuals. And the soft layers such as the file system and operating systems also affects the seek cost. So our solution is to perform seek cost evaluations in real environment. We random select some files on HDFS and perform seek operations on in the files, and record the seek time of each seek operation. And then we fill the seek cost function with the records. This is an example. We perform the seek evaluation on 3 types of HDDs. And the blue line, the red line is an theoretical seek cost function in hardware papers. So we have the accurate seek cost function, and we try to find algorithms for column ordering. The first type of algorithm we can use is enumeration, but the complexity is not acceptable when there are hundreds or thousands of columns. Then we try to use heuristic algorithms. We have mental heuristic algorithms such as genetic algorithm or simulated annealing. And we have some greedy algorithms such as hill climbing and autopart. These 2 algorithms are the vertical partitioning algorithm used in traditional RDBMS. They partition a table, the columns into several groups, so that each group can be accessed by a group of query, and the query latency can be reduced. So for the three type of algorithms, we have some experimental evaluations. The data and workload we use comes from Microsoft Bing search log. The column contains more than 1,000 columns, and the query workload contains more than 4,000 queries. There are 5 terabytes new data comes every day, so it's very expensive. It's too expensive for us if to store the whole data on modern hardware such like SSDs. The query in the workload looks like this. Most of the queries are aggregation queries to do periodically data report. It has where predicates and a goodbye predicate, goodbye statement. Firstly, we compare genetic algorithms and simulated annealing. We can conclude that simulated annealing often converges to better solutions. And we compare the meta-heuristics with greedy algorithms. Here we use greedy algorithms named AutoParsC in our paper. It's the algorithm that combines AutoPart and hill climb. And SCOA is the column ordering algorithm based on simulated annealing. In the figure, we can see that the SCOA algorithm performs much better than the greedy algorithm. SCOA has more than 28 gain on average over AutoParsC and 65 gain on average over the default column order. We also perform evaluations in real production environments, because in real production environments, on each PC server, on each node, there are tens of cores and physical threads. So there will be tens of concurrent tasks executing when the query is running. We can see in the first figure that it's the effects of concurrent reading tasks. We can see that even with tens or even hundreds of concurrent reading tasks, the gain of column ordering remains stable. And in the next figure, we can see that when the cluster scales out with 63 servers in the cluster, the gain of column ordering remains stable. And we have some further improvement on column ordering, because there are some hot columns which are accessed by many groups of queries. For example, in the figure, column 1 is wanted by query 1 and query 3. If we have a replica of query 1, then we have a replica of column 1. Then query 1 and query 3 will both be happy. The first problem we have to solve is to find such hot columns. Actually, the frequent accessed columns are not to be sure to be the hot columns, because a column can be frequently accessed by just one group of queries, and it's not hot. The hotness of columns is defined like can be defined like this. For example, for column 6, we find the queries access this column. That's Q2 and Q3. And for each query, we find the previous and successive query column of column 6. That's C3 and C9. Then we calculate the seek cost from C3 to C6 and from C6 to C9. And the hotness of C6 is 5. And similarly, for column 1, we can find the queries access these columns and find the neighbors of it and calculate the hotness of column 1. Then our column duplication algorithm is just enumerating all the possible positions to insert these hot columns into the column order. And we can have 12% actual gain with 5% storage headroom. But there are some side effects of column duplication. The first side effect is that we have to rewrite the queries because there are some replicas of the columns. So the query has to be, the columns in the query has to be redirected to the replicas. The query is rewritten like this. And the first side effect is column duplication increase the data loading time because we have more columns in the schema. And when loading the time, we have to calculate the column format. We have to compress the columns, so we spend more time on it. And we design adaptive layout optimization framework. This is used in production in Microsoft. In this framework, we do not need to change the source code of data analytical systems such as Spark and the distributed file systems. The framework implemented works just like apart from the existing systems. It collects the query and calculates the optimized layout for the system. And this is the source code of our system. And thanks. Any questions?
Thanks. I'm a little bit confused about certain things about your design. So you're using HDFS, which is a distributed file system.
Yes.
Yet you are sequentially or serially reading these columns within a query, right?
Yes.
But I would have imagined that you want to actually distribute these columns across the nodes in the HDFS and sort of like read them in parallel, right? So which would completely get rid of the seek latency.
Yes, this is a very good question. Actually, there are parallel tasks in HDFS in environment when executing queries, but the conflicts of the concurrent tasks is not very large because for each task it reads one HDFS block, and the block is stored continuously on the hard disk. So when a task is reading the block, the other task is hard to compete with it. It will read a sequential part from the file. So we have an experimental evaluation with concurrent tasks. It shows that it does not matter. Yes.
So I was just wondering, did you consider to exploit the existing replication for this column duplication? I mean, all those individual blocks are anyway replicated 3 times, right? Now, conceptually, you have the chance for each and every replicate to use different orders, right? So I'm just wondering, how hard would it be to exploit the existing replication factor instead of explicitly duplicating those individual columns?
Yeah, so good question. Actually, there are existing works to use different column layout in the 3 replicas. But if you do this, you need to change the source code of HDFS, and this is not acceptable in many production environment. So but we can do this if we want. Actually, with more, if you have 3 column layout, you can select the best column layout for a query. There will be more opportunities for you to improve the query performance. Yes, thank you.
So I have a question. Did you consider a lot of these log formats are semi-structured formats like JSON or XML or Parquet and so on, and except for the columnar ones like Parquet, a lot of these already sort of co-locate their columns based on the substructures that are there that are commonly pulled out. So right now you just assume that you have 1,000 columns that are completely flat, but in many cases you actually have commonly accessed columns already packed together in substructures within the file. So did you take that into account when you were developing these algorithms, or these things are just entirely independent?
We haven't considered this in our solution, but actually for file formats like Parquet, the column, the structure such as JSON or a map or array list is stored as a flat column order. Yes, it's flatted in Parquet, and queries will maybe access the columns together. So if there's such pattern, it should be considered in column ordering. Okay. Thank you.
So next we have Tillman, and he'll be telling us about how we can build partially replicated database systems. Thanks.
Okay, thanks a lot. Okay, you can hear me. Perfect. So this is work on a query-centric partitioning and allocation strategy for partially replicated database systems. And I work at the Technische Universität Berlin. And this is joint work with my previous co-advisor, Hans-Arne Jacobsen from the Middleware Systems Research Group. And so as a bit of a motivation, think about building a new e-learning platform or website, which is super innovative and, of course, let me try this, backed by a database. And since it's good, you have an increasing number of users. and increasing data and workload, and eventually this grows beyond the capacity of a single node. So, of course, what to do? We have to scale our system. Two options here: either scale up, which in many cases is good, and we've seen in the keynotes that you can get huge machines today, which will probably last for e-learning platform forever, but it's also very costly, and in many cases cost prohibitive. So in many cases you want to scale out, but not to hundreds of nodes, but a couple of nodes, and you need a system that actually does scaling fairly early. So you don't want to like put 10 nodes in order to get scalability. And I mean, the most common architecture for this would be a shared nothing architecture. So you have many standalone databases basically connected to some kind of master, and the master has a connection to clients. So this is the most simple form of building this. And in order to scale this, it's important to have a good data layout. And there's different options that you have. You can do replication, which is great if you're just having read access. You can do sharding if you know your data well and it's easy to separate in different parts. You can do declustering if you have like a more tightly integrated system, and then randomly or in a round-robin fashion distribute your data. Or you can do partial replication, which typically gives you the option to do a good load balancing across your system. And this is actually what we want to do. We want to build an allocation that is load balanced and throughput optimized in a shared nothing database. So there's a couple of things to consider. And one thing is read queries are embarrassingly parallel. So if you do full replication, basically this means that you get a perfect speed up. So by just adding more nodes, you get a speed up of the number of nodes. But on the other hand, write requests is of course not embarrassingly parallel. So if you do more replication of the write requests, this means the updates have to be processed on all the replicas affected. And this will reduce your throughput actually. And so this is basically the trade-off that we're working with, is in order to increase the performance, increase the throughput, while decreasing the write replication in the system. And for this, we've built an automatic allocation strategy, which can do all of the steps required completely, fully automatically. And this is more or less a three-step procedure. There's a couple of additional things that I cannot touch on because of the interest of time. And you can look at the paper to get the details. But in the next couple of slides, I'll walk you basically through these 3 steps, and then I'll show you experiments on how this is, or how well this performs. So in the first step, we have classification, which basically gives us an implicit partitioning of the data. We use this implicit partitioning to actually partition the data and calculate an allocation. This can be done optimally, so using a linear program or heuristically. And we distinguish between read-only and write-heavy workloads, or workloads with updates. And then after calculating an allocation, it has to be somehow implemented into an existing system. This also allows us to do like scaling of systems, etc. So let's go through the individual steps. So the first step is the classification. And what we do is a data-based classification, meaning we look at the references of the queries in our query profile, and these references will create our, basically will classify these queries. And we can do this in different granularities. So the simplest thing would be looking at the tables. So say we have these 3 examples here: insert X into A, meaning this is an insert class on table A, so let's call it class A. And we have 2 selections on the table B, which would be class B, and we differentiate between updates and selects. And as I said, we could also do this on the columns or on the predicates. And based on this, we can generate a query profile, which is basically the set of all these query classes. And for each of these query classes, we calculate the weight of these query classes, basically looking at the query profile, looking at the queries before, either the execution time or looking at the optimizer's cost. So both is possible. And one thing to note is that the query sets are disjoint in these query classes, but the data does not need to be disjoint. So we could have a query that selects from table A and B, and on the other hand, we can have a query that selects from table A, and meaning that we have a query class that references A and a query class that references A and B, but these will have disjoint tables. Then based on this, we can calculate the allocation. This is, in general, NP hard if we want to do it correctly, when you can basically reduce this to bin packing. So we create a first fit strategy, and so I will show this in an example, so you don't have to read the code now. And for the example, we consider having 4 backends. So 4 databases in a homogeneous setup. We also have inhomogeneous setups in the paper. So here, each of the backends would process 25% of the data. And we have 7 query classes, 4 read query classes, 3 write query classes. So for example, the A query class is 24% of the workload. And we also have a query class that selects from A and B. And we have 3 update query classes, so A, B, and C. And the first step in our allocation is we have to combine the read and write query classes. And this is because whenever we allocate any kind of reads to a backend, we also have to submit all of the writes or updates to this backend. So this will be our first step. Looking at query class A, for example, so the read query class, meaning if we put any workload of the query class A on a backend, we also have to allocate the complete update workload for A on this backend. So this would be our first, and we do this for all of the query classes. And we can see that here already we have some redundancy. So for the query class AB, we also have to, again, allocate the update classes for A and B. And then in the next step, we will sort these query classes based on their weight and size. So meaning we want to allocate larger query classes that have like many tables or large tables to allocate, and that have a lot of workload to allocate. We will allocate these first. So in our case, looking at the numbers, this will be class AB first, then B, then A, and then C. And we could have additional update classes that are not connected to any of the read query classes. Then these would also just be sorted in there. And as a next step, we start searching for nodes. So we will start allocating these query classes individually. First, we start searching for a node with a similar allocation. Since everything is still empty, it will just be the first node which we pick. And we start allocating all of the write load. So as I said, this always has to be done, since the node will see all of the updates of the data. And this basically already fills 14% of our node. And then we write we add all of the read workload, or as much of the read workload that we have in this, that we can fit on this node, we will fit on this node. So in this case, you can see we put the class AB on the node, but we cannot allocate the full workload of this node. But we can, or the full workload of this query class, but only 11% of the 16%. And we do the same for all of the other query classes. So basically the greedy heuristic continues. We do this for B, A, and C. And then we see all of the backends are actually full, and we still have workload to allocate. So in this case, we start increasing the capacity of all nodes. And by doing so, we can allocate the rest of the nodes. And finally, or the rest of the workload. And finally, after doing this, we have the complete allocation. And this is basically what the greedy heuristic does. And so we can look at our final allocation that was computed. And in this case, it actually is an optimal allocation, which does not necessarily have to be. And you can see the optimal allocation has a varying workload. So this will be a throughput optimal allocation. In our case, it has a varying workload from 23 to 26% that the nodes see. But this is actually, if we would try to further balance the workload, it would mean we have to duplicate some of the or further replicate some of the updates, which then would decrease the total work, the total throughput of the system. So as an example, and actually we can easily calculate in our model the expected speed up. So if we look at the maximum load, we can see that AB and the node 1 and node 2 have 30% of the workload. And if we divide 1 divided by the maximum load, we get the expected speed up, which would be 3.3. And we will later see that this is actually fairly close to the real speed up that we get in our system. And if we, for example, would do a full replication, this would mean we have 20% of updates on each of the nodes. And then we will see an expected throughput of the system of 2.5. And after certain scaling, we will actually see that we will see a slowdown rather than getting additional performance in larger scales for full replication, which also is to be expected. Okay, so we have the allocation. The last step is implementing the allocation on an existing system. So if it's empty, of course it's easy, but often we have already an allocation in our system because either we change the setup, we add more nodes, or we somehow the workload changed, for example. And what we can do is we can do basically, you look at our new allocation and the old existing allocation. So in this case, for example, we might have scaled up our system, added an additional node. And in order to implement this, we can see this as an assignment problem. So graph matching between the new allocation and the old allocation. We do a complete bipartite graph between the two, label the edges with the cost of implementing the allocation on one of the nodes. So say the first node on of the new allocation on the old allocation would cost nothing because it remains the same. If we move it anywhere else, it's in the order of the size of the table, basically. And using the Hungarian method, we can calculate an optimal solution in cubic time, which in this case, for example, will be in the order of AC if we allocate the second node to the third node. So all of this was implemented in a prototype where we had Postgres databases as backends. And you can see the architecture on the right side. So at the center, we have a scheduler, which basically schedules, which is the master in the system, schedules the queries from the driver to queues. And we're using a least pending request first queue, meaning that each of the nodes, or if we have a choice of sending a query to different nodes, it will be sent to the node with the least workload or least pending requests. And we do a ROVA scheduling, or read once, write all scheduling, meaning that read requests will only go to one node, while write requests will go to all of the nodes. This was implemented and tested on a 10-node cluster with 2 quad-core processors, 16 gigabytes of RAM, 10 gigabyte Ethernet, and each node had 2 74 gigabyte hard drives with RAID 0 configuration. And we tested it on 2 benchmarks, TPCH for online analytical processing, and we only used the read part, so only read workload. And 3 of the queries were actually so prohibitively slow in Postgres that we omitted them. And we tested it for scale factor 1, 3, 10, and 30, resulting in 1 to 30 gigabytes. And we also implemented or tested TPC up, which is an online transaction processing workload. And basically simulates an online book reseller. And in this case, we have more queries, approximately 40, and we tested it with 300 emulated browsers and 12,000 emulated browsers, resulting in 300 megabytes and 8 gigabytes of data. And let's look at the throughput. So in the TPCH setup, we see what we expect, more or less. So we see a linear speedup, which is similar to the full replication. So if we do full replication, of course, we're going to get linear speedup, since we can just distribute all of the workload across all of the node. But for our table-based allocation, we see the same, and for the column-based allocation, we actually see a slightly hyperlinear speedup. And this is because we're going to see reduced I/O costs on the nodes, because the column-based allocation will benefit from the typical column store layouts. And overall, this is very stable. So we only see 6% deviation in the throughput if we, or in the experiments, if we run these experiments multiple times. So each of the experiments was run 10 times. And yeah, for comparison, we also implemented a random allocation where we would make sure that each of the nodes or each of the queries can actually be executed, but we would not care how the workload is distributed across the nodes. And there you can see that this fairly quickly flattens out at a throughput or a speed of about 2.5. And yeah, we also scaled this up to larger scale factors. And here you can see that this is basically gives us the same kind of behavior. And we also, like here's for scale factor 1 and 10. And we also saw similar results for 3 and 30. But for 30, again, we had to reduce the number of queries because Postgres would just get way too slow in answering these queries. So if we look at the read and write workloads, so from TPC up, this is actually a bit more interesting because there we get this additional replication, meaning that some of the, like if we want to scale it up, if we just replicate the data, if we do a full replication, we're not going to get a full, very good speed up. And this can actually be seen in the results. So here we have a read to write workload ratio of 3:1 in terms of workload, not in terms of number of queries. And if we calculate, based on the previous calculations, if we calculate the maximum throughput that we're expecting, we see maximum speed up of 7.7. And in the actual experiments, we see the maximum speed up of 6.7. So this is actually fairly good, I think. And for the full replication, that you can see that after 5 nodes or 5 backends, it actually flattens out. You don't get any performance improvements anymore. And towards the 10 nodes, you can slightly see that it actually decreases in performance, while the column-based and table-based allocations both still have good speed ups for increasing number of nodes. And we also did the same thing for larger setups. And here you can see that the performance actually degrades a lot for the full replication. So you actually see a slowdown for full replication, while column and table-based allocation will still speed up. And with this, actually, I'm already at my conclusion. So I presented you a processing and performance model for partially replicated database management systems. More on the model is actually in the paper, but it allows an accurate throughput estimation, and it enables an automatic allocation. And this is what I mainly showed you today, the automatic allocation strategy, which has a good scaling behavior for shared nothing, partially replicated database systems. It's good for analytical and transactional workloads, and it's also extensible. And this I did not mention in my slides, but there's more in the paper that we can do. Like we can additionally increase the robustness of the allocation. We have a strategy for case safety. So if multiple nodes die, we can make sure that the system will still continue to work. And we can also do automatic scaling, meaning if you see more workload, if you see changed workload, we can change and adapt the size of the cluster and do additional rebalancing. And for future work, we're going to look at additional partitioning strategies and also at individual query execution times, because this is something where this strategy is right now, or the model, which is not reflected by the model right now. If you have very long-running queries, the allocation strategy will actually think that it can partition it across nodes, which the system will not be able to do. So with that, thank you very much. Any questions?
Thank you. A couple of questions. So full replication doesn't have pretty much the same result for the reads, but has the slowdown for the writes, as you mentioned. So what kind of replication you consider, do you mean that the data has to be replicated to all the nodes or only one? Because it gives you a little weaker guarantees. And in this case, I don't expect any slowdown because you still have to write at one place. That's number one. Second, replication is data redundancy. If it's full replication, provides you additional guarantees that if one of those nodes which goes down, then you still have reserve copy and you can just fail over to this node and keep going. So what are the guarantees you have with your model, given that it's a partial one? And RAID 0, which you use for your setup, doesn't provide fault tolerance. Thank you.
Right. That's true. So maybe let me start with the last. So RAID 0 was really just because the cluster was set up that way, and it's for the prototype. So that doesn't really make any difference for the system. With full replication, I mean that really all of the nodes have redundant data. And in this case, you get a perfect speed up for read-only workloads. So this is basically what we compare against to in a setup where we have a read-only workload. So we want to be as fast as a full replication in a read-only workload. If you have writes, this basically means, or updates, this basically means you have to replicate them across the system, and this is why you get a slowdown. Yeah?
Yeah, so an alternative is to take your e-learning application and run it on a cloud database like the ones on Amazon, and they provide elasticity and all that. How close do they come to the level of optimality that you need? Why do you bother with all of this stuff when you could probably use it and use the other alternatives?
Well, I think it's, so the question is basically why bother with partitioning in the first place and not just use a cloud setup?
Yeah, the question is elasticity over here.
Yeah.
Right?
So
I mean, nowadays one should look
right.
at those
I mean,
other ones.
it is an elastic approach. If you use the cloud and if you use individual instances, you still have to somehow, okay. Right, but then you, right. I mean, you can also use this kind of replication strategy in the cloud, basically.
Why do you want to do that when it's much easier to just let them?
Well, then let them do this replication strategy.
Yeah, that's what
Yeah, so that would be one option. So they implement this, yeah, okay. Yeah, this would be an option. So maybe also regarding the, I think I didn't fully cover the first question regarding fault tolerance. And so there we have an additional algorithm or an extension of the algorithm where we make sure that either each of the data fragments or each of the query classes will be replicated k+1 times. And this means that k nodes can fail, and then we will still have fault tolerance in this case. Okay? Any other questions?
And now we'll have Sergey tell us how they turned Spanner into a SQL system.
Okay. Can you hear me? All the way in the back? Excellent. My name is Sergey Melnik. I'm here on behalf of a large distributed team of people who built this distributed system called Spanner. And the team itself is distributed 4 ways across Mountain View, California, New York, Seattle, Kirkland, and Dublin. And a large portion of what I'm going to be talking about was done in the Seattle, Kirkland campus. This is where I'm from, and a few colleagues of mine are also here with me, and I'm sure we'll be happy to chat with you and answer questions and the poster session. Spanner is a distributed DBMS. It backs many mission-critical services at Google. including AdWords, Google Play. It processes tens of millions of requests per second over thousands of databases. It runs as a globally replicated, highly available managed service. And it is publicly available on the Google Cloud platform. As a matter of fact, just a few hours ago, it has been announced that Spanner went out of beta and entered general availability. And I must say that this is the cloud. We have a subset of features, and the internal version of Spanner has some more functionality that I will be talking about in this talk as well. This talk is about making Spanner a SQL DBMS, and it builds heavily on the work that we presented at OSDI 12 that covered ACID transactions, replication, and fault tolerance. All right. Here's the agenda for today. I'm going to start with a background on Spanner. That's essential for the rest of this talk. Then I'll talk about the SQL interface that we offer and spend the bulk of my talk on distributed query processing. And finally, I'll wrap up with lessons learned. There's one topic that I omitted from this talk due to time constraints on blockwise columnar storage that you can find in the paper. Spanner presents itself to the users using a familiar relational surface. Here's an example of a Spanner schema. It's a tiny schema with some populated data that you see on the right-hand side. And you see here two tables, singers and albums. And later on during this talk, I will be using this schema to illustrate some of the query processing capabilities. The singers table has a single primary key called singer ID. It's an Int64, and it has a payload, the singer name. Albums has a composite primary key. It has a singer ID and album ID, and stores album titles. So on the right, you see some data instances. That's for the singers table. It has, for example, singer ID 1, singer name Beatles. And these are the albums that correspond to Beatles, album 1 and 2, Help, and Abbey Road. There is one thing that I'd like to point out here, which is quite important, is that interleave in statement. And I'm going to explain what it means on this second slide. But first, let me talk about sharding. Spanner is a sharded database. You can think of a shard as a horizontal slice of a database. And Spanner uses key range partitioning. So in this example, I've decided to chop up our small data set into two shards, shard 1 and shard 2, where shard 1 stores all rows with singer IDs below 3. And shard 2 stores all rows with singer ID equals to 3 or higher. Now, this previous statement that I showed you, interleave in, controls collocation. What it means is that interleaved rows it means that all rows that agree on singer ID are guaranteed to be stored in the same shard. So in this example, for instance, Beatles and the albums corresponding to Beatles will be collocated, which means that we don't have to do a two-phase commit. We don't have to run distributed transactions if we're accessing these rows together. As a matter of fact, another form of getting the data closer is physical interleaving on the data. And this is illustrated in this example, in fact, that all rows corresponding to the Beatles are stored right there next to the Beatles row. And this further increases data locality for access. Shards themselves are replicated. Here, our shards 1 and shard 2, are both three-way replicated across 3 clusters. Replications uses Paxos and several synchronous and asynchronous replication protocols. There is one special kind of replica that Spanner uses. It's called leader. Leaders are responsible for writes. So in this case, we have the leader for shard 1 running in cluster 1. The leader for shard 2 is running in cluster 2. They can also serve reads. And we also have non-leader replicas, whose primary goal is to serve reads. They can sometimes become leaders. Not all non-leader replicas can. And they may be behind. They may be behind, especially if asynchronous replication is used. So in this example, we have really a minimal set of replicas that are needed for Paxos. But we could also have more. Asynchronous replicas, for example, for high availability. And this is an example of replica placement. So once we have sharded and replicated the database, we can allocate the replicas around the world. This is an example of geo-replication for a mission-critical database at Google. This is done for high availability and also for the ability to process a lot of requests. Spanner has, in terms of transactions, Spanner supports both pessimistic locking and a versioned scheme, multi-version concurrency control. It offers a very strong form of consistency called external consistency. Essentially, it respects wall-time order of transactions globally. This is done as a combination of hardware and software solution using atomic clocks and GPS clocks. And this was covered in the OSDI paper in more detail. There are two kinds of transactions. One is snapshot, another one is read-write. Snapshot transactions are non-blocking. They do not interfere with writes. And they always see a consistent state of a database. So every read happens at some timestamp t, and at that timestamp, every query will see a consistent state of the entire database across all shards of the database. There are two forms of reads. There are strong reads and stale reads. Strong reads see the effects of all transactions that happened up to now that this request was sent out. And stale reads are allowed to pick the timestamp t at which they see a snapshot a little bit in the past, within the bounded time frame that is specified as part of the request. Read-write transactions, one peculiarity about them is that all writes in Spanner get buffered and committed at the end of the transaction. All right. Next, I'm going to switch gears and talk about the SQL interface. When we started designing the SQL surface for Spanner, we were driven by three requirements. First of all, we wanted the SQL dialect we support to be standards compliant. Second is the type system that we use, we wanted to align better with programming languages, especially scalar types such as Int64, float, UTF-8 strings that you find in programming languages to avoid the impedance mismatch between applications and the database. And third, Spanner's SQL dialect offers first-class support for nested data. In particular, it supports later SQL standard types called array and row types natively. And also supports protocol buffers, which are essentially schematized binary objects which are currently deployed only in the internal version of Spanner. So fulfilling these three requirements took a lot of design work across several teams at Google, and the net effect of this is that we now have a SQL dialect that's shared across several systems at Google, including BigQuery, Cloud BigQuery, /Dremel. Dremel is the internal product corresponding to BigQuery. The F1 system that's used in the ads organization, and several others. This is actually quite tricky to get these systems on the same page, and I'm going to be talking about it a little bit in a minute. But first, let me give you an example of a query that Spanner can execute, and later on I'm going to show you how we actually support distributed execution of such queries. In this query, you see it essentially selects all singers and the corresponding albums for these singers. You see that there is an outer select from where statement that goes over all singers with singer ID between 1 and 5. And there is a correlated array subquery in the select class. This correlated subquery selects all album titles where the singer ID matches the correlated parameter singer ID that comes from the singers table. And this is an example of what we would get for this as a result of this query. We have, for example, Beatles comes back with an array of strings, help, and Abbey Road. And this is an example of where nesting makes it a lot easier to program applications because there are no auto joins that we need to do to get this data back. There are no multiple round trips. It's sort of easy to consume by applications. So keep this query in mind. I'm going to get back to it. But now let me talk a little bit about this challenge of getting the systems on the same page and making them speak the same SQL dialect. In order to get Spanner, BigQuery, and F1 and others to comply with the same semantics that we want, we built a solution that consists of two parts. One part is shared code. So given a query, there is a shared library of components that parses this query and produces sort of like an algebraic representation of it, which is then consumed by all of these systems. It's sort of kind of a first level of getting a system on the same page. Second is, sort of part of it is an execution library that we built that encapsulates many tricky functions with various error semantics that will be shared across them as well. But a big part of what we have built is actually a compliance suite. This compliance suite consists of course, of a bunch of test queries and expected results, but also of a random query generator that runs billions of queries across all of these systems and compares their result to a result produced by a reference implementation. It's like a simple in-memory implementation of the language. And this helps us to keep these systems honest and is also contributes a big part to testing of these systems. Now let me talk about distributed execution in Spanner. Spanner is built using a tightly coupled architecture. The query processor runs inside the DBMS. And while it is a typical design for standalone DBMSs, it's actually not so for distributed systems. The biggest challenge probably that we had to solve is the challenge of scale and the fact that the data never sits still and is constantly moving. There is continuous resharding going on in the system due to various reasons. It could be load, capacity, configuration changes. Shard boundaries, importantly, may change even while a single query is running. Shards may become temporarily unavailable during execution, and there are lots of replicas to choose from. Some of them, these replicas can be close, some of them are far apart, some are loaded or idle, some are caught up, some are more behind. The mechanism that we built to address this challenge are the following, and that's what I'm going to spend some time talking about next. One is query routing. We use a special form of requests and query and range extraction to get queries to the right place. Second is parallelizing execution, which means that really our job is to take the amount of work specified by the query and partition it and parallelize it to the extent possible across servers. And third is dealing with failures. This is what I'll be describing under restartable query processing. So now let me cover these three bullets in a little more detail. Spanner routes requests to row ranges. It doesn't send them to servers, it sends them to a range of rows. So in this example, you see, for instance, if we have a condition on the primary key, singer ID is between some low and high parameter value. It specifies a range of keys that are present on some shards, and the job of this RPC mechanism is to find what shards to address and send the query there and not anywhere else. This mechanism hides the complexity of locating data and is designed to find the nearest sufficiently up-to-date replica for a given concurrency mode. It retries automatically in cases when data becomes unavailable or moves away or there's a scheme update. And the clients cache both the sharding information as well as what we call location hints for queries. So location hints are there to avoid multiple hops to get to the right destination. So we first analyze the query, extract like a concise representation of what table is referenced and what key we potentially should be looking for, and do it once and cache this information. And then when the query comes in with a query parameter, we don't have to analyze it. We just look at the parameters and we decide directly where to send it. Part of this query routing mechanism is what we call range extraction. So assume for a second that the albums table here is independently sharded. And the query has this predicate specified in the where clause. Now, range extraction allows us to look at this predicate at runtime and find all ranges of keys that are relevant for executing this query. In this example, this analysis yields 5 ranges. And we know that we just care about the shards that have those 5 key ranges and no other shards. This mechanism is also used for restricting scans. Obviously, so when the request gets to a shard, we want to scan the least amount of data necessary to answer this query. And as I said, this mechanism runs at runtime. It may actually access data to compute what data is needed. And you will find the details about it in the paper. The second bullet on distributed query execution is parallelism. Let me show you how we execute the query that I've illustrated before that selects singers and titles. For the sake of this example, assume that the shard boundaries are fixed during the execution of this query. And I'm going to talk about next what happens if they're not. So this is an initial logical plan that we create for this query. There's nothing surprising here. There's a scan of singers. There's a filter sitting on top. There's a correlated compute operation that creates this, calls this, materializes an array that itself comes from a scan of albums filtered by the singer IDs. Now, if you look at this, you see these 2 scans, and really, in reality, every table is sharded. So in order to make these plans operational, we have different distribution operators that we inject in query plans, and this is one of them. One of them is called distributed union. The job of the distributed union is to take a subquery, in this case it's simply a scan, and send it to a number of shards. Execute it there, get all the results back. So here, to make this plan sort of more executable, is this distributed union tells us send this scan to all shards of the singers table. This one, send it to all shards of the albums table. The dotted blue line here indicates server boundaries. So everything here happens on one machine. Everything here happens on different instances of other machines to which a request goes. Now, obviously, it's bad to send this query to all shards of the singers table. So a lot better plan would be if we move the distributed union higher up above the filter and push the filter down. So this way, we both push the work to the shards, and we can also, by using this filter expression, we can analyze it and extract ranges that we need to distribute over. So in this case, we can figure out that all singer IDs we care about are between 1 and 5. These are the only shards that we need. And so the same way the distributed union moves up for the albums on the right. Now, if you look at this, remember that the singers table and the albums table were collocated on the singer ID. We can exploit this information now to do even better than this plan by realizing that this is the same singer ID that's referenced in this distributed union as these ones, and moving this distributed union further up. Now what we have is a perfectly parallelizable plan where essentially the entire query will be shipped to the corresponding shards that have this data, and the result is going to be fed back to the client. We call this class of queries root partitionable, And as a matter of fact, there is a special API that Spanner offers internally to execute this query efficiently if there's a lot of data that needs to be consumed. So in this example, we would allocate a number of workers, 2 in this example, which will consume in parallel portions of this query result. The contract of this API is that these workers will see the same data as what we would get through the single consumer API if we were to use that, up to the order of rows. There are other distribution operators that we cover in the paper that I'm going to skip here. The third mechanism in query distribution I'd like to talk about is called query restarts, or restartable query execution. Query restarts is a mechanism for automatic compensation of failures, and it works only for snapshot queries in Spanner. The way it works is that when the result comes back in batches, the server attaches a restart token to every batch such that the client can take this restart token and continue execution from this point onward if something bad happens, and can do it transparently. Here is an example of the result that I showed you earlier for this query over names and titles. Suppose that the client started consuming the result, and you've seen a row on Beatles and Abbey Road, and now something happened, perhaps network partitioning, or the server got overloaded, and sort of internally there is a failure that came back. So instead of returning this failure back to the application, the client transparently retries and perhaps sends this request now to a different replica somewhere in a different data center. The contract of restarts is that it omits the rows that have been returned previously, but there is no repeatability guarantee for subsequent rows. So if this restart happens and the client resumes, it will see the remainder of the data without disruption. When we started implementing restarts, we found that naive solutions don't really work for large queries. So things like buffering results or persisting intermediate results, counting rows, they don't really work. Instead, what we do is we capture the distributed state of the query efficiently. There are 3 big challenges that arise in this context. One of them is due to dynamic resharding. So suppose that you have the distributed state, now you're trying to re-execute this query, but the data has shifted away underneath you or has been repartitioned. Another one is non-determinism, that's due to memory sizes, parallelism, computer architecture, and so forth. And the third is versioning. When the restart happens across server versions, then perhaps query plans might have changed from one version to the next, generated for the same query. Addressing these challenges is really complicated and deserves its own paper. And we found it to be really hard, but worth it. In particular because this mechanism hides transient failures. It takes out retry loops out of applications. It supports streaming pagination of results. Ensures forward progress of important class of long-running queries. So it's obvious for long-running queries if you kill it in the middle and try to re-execute it, maybe it won't complete the second time. But also for short-running queries, restarts are beneficial because they reduce the tail latency overall. And finally, Spanner gets updated on a 2 to 3 weekly cycle, the server fleet. So there's always something being upgraded at any point of time, really. And this mechanism allows us to do these rolling upgrades in the least invasive fashion possible. Okay, talking about lessons learned. There are a few aspects of the DBMS architecture that we had to rethink for scale. One is that Spanner runs exclusively as a service, and from day one, there's a huge economy of scale in centralizing human load. But running as a service also brings really hard challenges, as for example, to never regress, which makes query optimization especially hard. The second aspect is dynamic sharding, which is essential for elasticity, the ability to move data around at all times. Third is sending data to sending requests to data ranges as opposed to servers, it greatly reduces the complexity of internal communication and replica selection. Fourth is shard level isolation. Shards can become, in Spanner, a shard of a table can become unavailable without affecting the overall workload on other shards. This is especially important when data from different users get multiplexed into the same large table. And the fifth one is restartable snapshot queries that both increases the perception of robustness of the system and ensures forward progress in presence of failures. Stepping back, Spanner started out as a transactional NoSQL core whose focus was on horizontal scalability, which is essential web scale systems, manageability, which includes failover and easy resharding, and ACID transactions across arbitrary rows. The first user of Spanner was the F1 system built by the ads organization at Google. They essentially layered all the relational concepts, relational models, schema, SQL indexes, on top of Spanner as a separate service. Now we have spent the last few years of bringing in these the features of relational DBMS and baking them natively into Spanner. We both borrowed a lot of insight from the F1 team while doing this, and also leveraged the fact that the transactional core has been running in production for years, and if you have a massively scalable system, then a lot of things that can go wrong eventually do. So it helped iron out many bugs in the process. In terms of lessons learned, one thing that perhaps we could say is that both loosely coupled SQL designs and tightly coupled SQL designs work well. As a matter of fact, they can be deployed simultaneously on the same transactional NoSQL core, as in case of F1 and the native Spanner SQL. Second is that we found transactions to be immensely helpful for building the system internals. There are many processes in Spanner that happen related to data movement, schema versioning, online index creation, backups, format changes. All of these things are immensely complicated with transaction and really probably not doable without. Now, for folks who are building systems like Spanner, we would like to recommend to embrace the relational model as soon as possible, earlier rather than later. Both because well-known abstractions are understood by developers and help them get on the common page, and also to reduce the cost of foreseeable future migration. Finally, it is perhaps fair to say that SQL versus NoSQL dichotomy may no longer be relevant at Google. SQL and NoSQL can be viewed by developers as simply two different APIs through which we access the same transactional core, of course with vastly different capabilities, but eventually hitting the same system. That's all I have. I'd be happy to take questions. Yes, sir. Mohan.
Hi, Sergey. Nice presentation. One thing that wasn't clear is you said you are dividing up the query into ranges. I couldn't tell whether they are necessarily disjoint partitions or they may be overlap between those ranges.
So the shards themselves are disjoint.
That I understand,
Right.
yeah.
And so yes, so when we're extracting the ranges, we are indeed, yes, we are computing a disjoint range, disjoint set of intervals.
Is that easy to do when you have all these complicated things involving multiple?
It's not.
Okay.
That's why we actually decided to talk about it in this paper.
Okay.
And this is also especially hard because it cannot be done statically at compile time.
Right.
Because disjointness of ranges depends on query parameters.
Exactly.
So you might not know what overlaps, for instance, in this range and what not.
Okay.
It's a great question. Thank you.
So since that you are replicating data all around the world, so with these ranges, so what do you do about the data sovereignty?
Data sovereignty.
That means that some data cannot leave, for example, Germany.
Okay. So Spanner has a pretty sophisticated placement mechanism that allows us internally to specify where the data must live. I'm not sure to what extent it has been described in previous work, but it's something that Spanner is capable of addressing.
So is that defined outside the ranges, or some ranges are over here and some ranges are over there, and it's sort of transparent after that?
Right. So it's like a configuration process, right? So when you're designing an application and it has data placement constraints, then the data model used for that needs to be sort of so that you can actually formulate the constraints to place.
Okay, so you have to carefully choose your key ranges.
Absolutely. Schema design is actually a big, an important consideration.
Okay, so one quick question. What do you do with you support secondary indexes, and if yes, are they global or local to shards?
They're both. So there's a form of global indexes. And also, since Spanner supports collocation, right? So the index itself, the index itself can be collocated with the data that it indexes. So again, so it is by choice of primary keys, it is possible to index just, for example, one level down in the table.
But these are secondary indexes, not the primary. That's what my question.
Yes. So this will be a secondary index, but the secondary index will share a prefix of the key with the base table, and it can be declared as collocated with the primary with the base table.
Okay, got it.
Hi. So I think one of the things you didn't mention is how do you actually locate the data? So like you parse your query, you see your tables, your ranges, but how do you find where the data is on the cluster?
You mean the metadata itself, sort of how do we know what? Sorry. Well, I believe that the OSDI paper has some of these details. So Spanner itself manages its own metadata as a database of its own, really, which is also stored in Spanner. And the metadata can be very large, especially for large tables with, thousands of shards. It is really like yet another data set that can also be updated transactionally. So this is why when I mentioned that transactions are important, is that the placement information and where this data lives is also managed in the same consistent form internally.
Hi, I have two questions. Firstly, do you allow concurrent DMLs during resharding with the DMLs hitting the shard itself involved in the resharding? And secondly, do you have to have a primary key associated with the table schema for the purpose of hash-based sharding?
Well, so let me start with the second. Yes, you always have to have a primary key. Every table has to have a primary key. The sharding used in Spanner is range-based, right? So now, as to the first question, concurrent DML during resharding. Yes, Spanner, of course, does support read-write transactions while resharding is going on. Yes. Now, as far as DML is concerned, we do not expose the SQL DML API as a SQL DML. Right? Spanner has a separate API for writes, and in part this is due to this property that I mentioned, that all writes need to be applied at the end of the transaction. But this is one of the areas where, even though there is not a lot of demand internally for this feature, it's part of the standard, and we're longer term we'll be working on that.
Thank you for the presentation. I have two questions. First is, do you know the workload ratio between the SQL and the NoSQL interface? And the second question is, what kind of a join algorithm do you use?
What kind of join? Okay. Workload ratio, you mean the number of requests so that comes through the SQL API versus the NoSQL API? So yes, there is a, so NoSQL API has existed for a long time, for years. It precedes the SQL API. There is the majority of requests that come into Spanner go through the NoSQL API. Said that, the requests that I expressed in SQL usually do more work, or oftentimes a lot more work, right? So you can sometimes replace many NoSQL point lookups by one SQL query that does the same work, right? So it's not exactly apples to apples. And the second question was about joins. What kind of joins we support? So Spanner, we do support, like in terms of formulation of the joins, all the you know, the usual inner joins, outer joins, full outer joins, join methods. The work, so there are several of them. One is, so in sort of related to the distribution question that I brought up. A lot of the joins happen through what you can think of as a nested lookup join, nested remote lookup join, batch nested remote lookup join. We talk about it more in the paper. It's encapsulated in this distributed cross-apply operator. But we also support hash joins, of course. So these are the main algorithms.
Is it correct to say that most of your SQL syntax is intended for OLAP workload or OLTP as well?
It is actually primarily targeted at OLTP, right?
Okay.
Because Spanner is a transactional system. It's meant for operational data. But we have now a SQL dialect that's shared between Spanner and BigQuery. So BigQuery is Google's analytical product, and it uses the same query language.
But another storage, so or the same base storage.
No, it's completely different. It's a completely different system. It uses columnar storage. It's designed for scans.
I see. Yeah,
scans.
and the execution engine for Spanner is a row engine, not a column engine. Am I right?
Yes and no. So there is one aspect that I have omitted from the talk due to time constraints, which is about storage representation. And we have been working on making Spanner storage more suitable for database like access paths, as opposed to key value store access paths. And in part of doing this, essentially we're switching to a PAX layout, Alamaki's PAX layout, which is, you know, you have blocks, there's columnar representation inside the blocks, but again, it's for timestamp data, and we store large objects on the side. We try to move out all the versions out of the path of query execution. So that's sort of helps with OLTP as well.
For the automatic rebalancing of shards, is it based only on the size of the data, or do you use other considerations like the load or automatic co-location based on joins?
Yes, we do use load. There is a lot of consideration, a lot of attention pays to load. So you can have, like if you have a really hot row, for example, this one row may end up in a single shard. Okay.
So one question that I had over there was that, so if you have like the fact table, dimension table, so you have foreign keys over there referring to the primary key of another table, but that doesn't